actually did these applications graphically. They were exponential functions that we did, and we set the equation up. So I said if you wanted to get your equation and not have to redo that part, go back to your exponential packet that we had. We solved them graphically. Now we can solve them algebraically, because what happens is we have a variable in our exponent. The only way to get that variable down is that power log rule. That's what's going to bring it down. But the only way to get that down is to make this say log and bring it down. So we've got to have a log out here. Now, technically, you could start just like this, because this guy belongs to him only. It's the first one that they belong to, not the second one. This is only a 1, so that really doesn't matter there. So just get rid of your 1, actually. So technically, we already have one term here, one term here. Take the log of both terms. Now, this forces this to come down in front. That's your power log rule. You want to solve for t. It's being multiplied 4 times t times the log of that mess. Whatever that is, we're just going to throw it in your calculator. So we're going to divide by those two things. Now, here's an issue, is your calculator. If you use the alpha key, the alpha fraction key, not a problem, wherever that fraction key is. Not a problem. It handles this for you. If you have the 83s, or you don't have the software that gives you the fraction, you have to put this in parentheses. Because otherwise it's saying log 2 divided by 4 times the log of this mess. It's doing this first. And then it's going to multiply by that. So most important here is your parentheses. You want to use your power rule to bring that exponent down. And it should be the exact same answer as when we did this graphically. Graphically, we did this. It increased where this is. We doubled. When was it? So we did an intersect. So this time around, you need to bring that exponent down. And a log brings that exponent down. And yep, this is kind of a mess in here. Just leave it like that. Don't resolve anything until the very end. Sometimes it will be terminating. Let me see if this one terminates. I don't know. I usually don't even check it. I usually just leave mine. It does terminate into a very large number. So if you wanted to replace this with 1.014375, it did terminate. I would just kind of leave it, that whole thing, and you don't even have to check it to save. You found it? Okay, good. All right? God bless. All right. Questions? Give me any questions that you have, okay? Otherwise, we'll move on. Okay, maybe these kind of problems, you can see them a little bit better. So way back in our exponential package, and we'll just write this over again, in case you don't remember, because you're going to have to write your equation on this test anyway. So we assume that the bacteria doubles. We started like this. This is where my rate goes. This is my initial value. This is my time. So we're going to double. There's my double. Every 3 hours. If I put X represents hours. But I'm going to go every 3 hours. So how do I say that? X over 3. There's my cycle. And there are 2,500 units of bacteria that I start with. There's my equation. I want to know when is what I need to know, my exponent variable, when my bacteria will reach 100,000. Now, we did this in our calculator, and we saw when did they intersect, and we found when. Now, if we do this algebraically, remember, this is key. This exponent only belongs to that 2. Do not multiply 2,500 times 2. Then your answer is way, way off. It only belongs to this 2. Now we said, all right, let's see if we can isolate that part with the variable. So we divided by 2,500. If it goes in nicely, yeah, and divide. This one happened to go in exactly 40 times. Now you're to the point where the only thing that's going to bring down that variable in my exponent is a log statement. So I have to put logs on both sides in order to be able to do it. I can't put it on one side because it's an equation. Whether you put logs or ln's, they work the same exact way. Just put the log on both sides. Then this exponent comes down right here. I used ln, I interchanged them so that you can see you can interchange them. Now, I need to solve for this guy x. He's divided by 3 right now. What can I do to x divided by 3 to get it to be just plain x? Multiply it by 3. So let's do that. Let's multiply this side by 3, this side by 3. Get rid of your fraction. I need to solve for x. Oh, it's being multiplied by log 2. Divide by log 2. Don't divide 40 divided by 2. 40 belongs to the word log. 2 belongs to the word log. Try it in your calculator. Do log 40 divided by log 2. See if it's the same as log 20. It's not. So you need to see for yourself. You can't do that. Log 40 divided by log 2 is not the same as log 20. Okay, so make sure you put this in your calculator. Oh, where's my 3? Sorry, my 3. But I just wanted you to make sure, without the 3 here, I wanted to show you that this is not the same. Oh, aside from that problem. So make sure you put this in. You don't actually need a separate set of parentheses in here because order of operations will do the numerator first. We'll multiply that first and then we'll divide. We can all bring this log statement down. We can bring that exponent down with our power log. Okay.
So that's the formula you use every time. That's what we're using names.
Well, the formula itself,
Yeah,
all your formulas work off of this. Okay. Let me just see if I have a space down here we can work off of this. And it's probably a good idea to go through that because you're going to have to make your own formula. I'll put it right up here. All your formulas work off of this. Where this is my rate, this is my initial value, this is what I am accruing, what it's going to be when all this is said and done, and this is generally my time. Now, when you do a compound money problem, it's a little tiny bit different. It still follows this format, believe it or not, because watch, it looks like this, when you compound your money. Here's my principal, here's my rate, here's my time, but we also have a compounding factor in there.
That's only for money.
That's only for money. Everything else still, it still works off of this. It says, say I want to double something, then B is a 2. If I want to take a half-life, B is a half. Half-life, half of it. If I want to, like there was a problem that we did where we wanted to reduce our population by like 5%, let's say 5% a year. How do I represent my rate to say take away 5% a year? I do it this way, 1 minus R. If I want to increase, then I'm doing 1 plus R. But it all works off of this. The X is every month, every year, every day, every second. If I'm doing it in a cycle every 3 days, every 10 seconds, then I'm going to make it divided by whatever my cycle is. But they all work the basic format. It's just the only difference with the n is, with the compounding, is the n. See it? Here, this is where we did your population. Your population did this. This was increasing my population. This was compounding my money. Do you see the only difference? The only difference is n. It still follows the same format. But only use n when you're compounding money. And obviously our other one is Kurt. That works a little bit differently. Kurt is a continuous. That works differently. It still is my A, my B, my X. It still is the same thing. Principal, but the E is a little different. The E is my continuously, technically. All right? So they all work off of that. So let's take a look at your rabbits. Your rabbits started at 20. I'm going to fill this all in. I started with 20 rabbits. What am I doing to them? Doubling. That's double. There's my rate. Every month. So X represents every month, right? When my answer is X equals, will be months. I want to know, when will this reach? When is my time? When is this guy? 10,000. Now, remember your exponent only belongs to that too. So what am I going to do first? Circle this part. Go like this. I need that by itself. What do I got to get rid of? The 20. So since they're multiplied, let me divide by 20. So now I made my life very nice and simple. How do I bring down that exponent? A log. So I take, there's no log. So I put a log on this side, and then therefore I have to put a log on this side. It's an equal sign. It was that property, when we did your properties, it said x equals y, then we said log x equals log y. Same thing. I could put an ln if I want to. Now I use my power rule to bring down that exponent. And I can divide both sides by log 2. And I'll get what my x is equal to. And my answer will be months, because it asks me every month. You don't have to convert this to years, because it can be every month, every day, every second, every year, every decade. Whatever the every is my variable. If it's a cycle, every 10 days, then I got to divide it by 10. But they work right off of this guy. Good? Okay. Here's your half-life. So now your rate is going to be a half. Your rate says, okay, give me a half all the time. Now, I'm working in days. So let's start this for a second. I'm working in days. That would say every day. But when's my half-life occurring? Every 14. There's my cycle. I started out with 6.58 grams. And I want to know, when do I get less than 1? So I'm just going to set it equal to 1 right now. Now, let's do it the way you've been doing this, and we'll go back to this one in a second. We said this only belongs to this guy. So what did we have to do to the 6.58? Let's divide it. Yeah, it's kind of not the right way to do this, but we can do this, as long as we don't round in between. Okay, so let's look like this for a minute. Now, I've got an exponent sitting, I got a variable sitting in my exponent. The only thing that's going to let me bring that down is a log. So I need to put logs on both sides. ln or logs, whichever one you like. So I'm going to take this exponent, I can't separate it from the 14 yet, and just bring it down. the log 1/2 in my calculator. I can do the log of 1 divided by 6.58 in my calculator. That's not a problem. It's not really technically right to leave it 6.58 underneath the radical, underneath the fraction, but it's okay. I'm not leaving my answer like that. So, but what's troubling to me is this x. I needed to say x times something. I've got x divided by 14. So how should I get rid of that fraction? Times it by 14. Times both sides by 14. So now I've got 14, the log of 6.5, 1 divided by 6.58 equals x times the log of 1/2. And I'm going to divide both sides by, whoops, what happened here? It should say 14. I'm going to divide both sides by the log of 1/2. So in your calculator, you're going to say 14 times the log of 1 divided by 6.58. We're not leaving our answer there, we're just using it. Divided by the log of 1/2. And your order of operations will work for you because your numerator is going to multiply first and then divide. So try that way first and make sure you can do that way first. Now, I did this out the long way. Technically, we should not leave a decimal in our fraction, but we're not leaving our answer like that, so you still could do that. Technically, you should be able to say this works absolutely fine, and this is the correct way to do them all. Take the log of both sides. This is a product. So your product rule says, turn this into an add. Multiply everybody by 14. Then isolate this guy. So we're going to subtract that. It just makes your divide a little messier. We're going to subtract that and then divide by 1/2. But it gives you the same exact answer. So if you're comfortable just leaving 1 divided by 6.58 until the very end, that's fine too. That's fine with me. Just whenever you do a division in between, hold off doing it. Just carry that messy looking thing with you until the very end and do all your rounding at once. That's what's most important, is that you round at once. But don't even bother looking them up because I want to come up with your equations. So, we have a scientist starts with 150 units of bacteria, and it triples every 6 hours. We need to know when, which is the time, it will reach 150,000 units. So, let's just start basic first. What's A? This is what he starts with initial. This is what he has initially. What's my rate? B. 3. What are we doing? Tripling. Okay. What's my time? Okay, if I do x, this says x is every hour, but it told me every 6 hours, so divide it by 6. And what's my y going to equal? Good. Now, if I graph this thing, yes, I'll see my increase. I'll set it equal to this. I'll find out when. But algebraically, I need to solve this using a log. That's the only thing that's going to bring my exponent down. So what should I do first? This only belongs to this guy right here. So what? Good. Divide by 150. Now that certainly looks like it's going to go in the right way, right? Divide that out. See what you get. 10,000. 1,000? Just 1,000, right? 1,000 makes life a lot simpler. Remember, the exponent only belonged to this one right here. Now what should I do? I have one term.
Convert it to logs.
Convert it to logs. I need to have a log word here so that I can pull down that variable. It doesn't matter if you use ln or logs. The only stipulation is when you have base E, you must use ln. So ln is kind of like the universal one. Now what? This is why I did this, so I can bring this down, right? I need to solve for x.
10 to the power of 6.
Should I multiply 6? This fraction right here is like saying x times 1/6. So I want to get rid of my denominator. I'm going to multiply both sides by 6. If you do one side, you have to do the other side. Demo. Divide by log 3. Okay? Tell me what x is equal to. Six point two. I got 37. Did you remember your 6? So be careful of your parentheses too, because your calculator gives you parentheses here. Make sure you closed off your log one.
No, I did.
Okay, let me come take a look.
Do you do alpha y equals? Because that's what I do, because they people do the regular divide.
No, I don't think that's what it is.
No, this one would work for the regular divide.
Oh, really? Oh, alpha y equals.
Okay, the log of 1,000.
That's just easy.
Oh, I wanted to see. Oh, you didn't. You cleared it? I cleared it. Okay. I'm sorry to put it in again. Let's say. You're still missing your 6. That's why. You're missing your 6. Now, what is the log of 1,000, by the way? Guys, what is the log of 1,000?
3.
3. Very good. Very good, because this is 1 times 10 to the third, and the log is an exponent. Log equals exponent. You must have been awake when I said that. I'm very happy. Very good. So, you put it in the calculator. Okay. Well, you just could have fooled me anyway. So 3 times 6 is 18 divided by the log of 3. That would also get that for you. But keep it like this. This is perfectly fine. Everybody okay with this?
Kind of makes sense to me.
It does, doesn't it?
It does.
The only thing that will bring your exponent down is a log rule. And you can only put logs on something if they're one term. You can't do it when there's a mess of things out there. And the thing to remember is, guys, this is really important, that your exponent only belongs to this 3. It doesn't belong to this factor, only to this 3. All right, so let's have you set up this next equation. Let's have you set that up. All right, start me off for an equation. What's A? 100,000. This is my original population. Am I increasing, decreasing, doubling, halving? I'm decreasing by a certain rate.
1 minus
Point what?
0.15.
0.15. Move your decimal place 2 positions to the left. Make sure you're getting me a decimal. What's my exponent? T or x. This is my time, right? And I want to know, when will this be what?
50,000.
50,000. Okay? Everybody good so far? All right? This belongs to this guy. This one's very nice and reducible. Can you do 1 minus 0.15? 0.85. This is what's retained. When you lose 15% of your population, when you lose 15% of anything, Think about it if you lost 15% of the dollar. How much do you lose if you lose 15% of the dollar? 15 cents. So then how much do you have in your hand then if you lost 15 cents? 85 cents. So when you're losing, decreasing, you're retaining 85 cents on that one. So we can start like this, maybe make life a little bit simpler. That belongs to this guy. What do we do with our 100,000? Divide. And what do we know this is going to come out to be? Half, 0.5. You can leave it as 0.5, you can leave it as a decimal, or you can leave it as a fraction 1/2. And so it didn't really matter what they told us they had. I'm still getting to a half. Okay. Thank you, I'm sorry, thank you. So now, how do I get that variable down?
It's going to be x log 0.85.
Okay, I'm going to take ln, is that okay?
Is there a difference?
No.
So like
No.
it's going to mean the same thing?
Yeah, the only thing is when you use a BASE, you have to use an ln.
Is this a base?
No, but you can do it whatever one you want. This is kind of like a universal. Question? All right, I used ln. If you look in most college books will use ln just because it is the universal and you can use it with anything. So it's kind of like a mindless thing, just put the ln in there. Just be careful, it also gives you the parentheses and you have to close that parentheses. ln is right under log.
So 4.265.
Yeah. They're losing 15% a year, right? They're losing 15% a year. That's a lot to lose. Okay? Are we good with these?